Good morning, everybody. We're going to start right away according to the computer clock here. And I'm going to start immediately sharing. We have been looking at fusion energy and we already produced an introduction suggesting that we have two ideas or two concepts in nature that we can imitate to achieve fusion on Earth. One of them is already implemented in thermonuclear weapons that we are going to describe today as the inertial confinement concept. And one concept in nature that we can got inspiration from in terms of achieving a controlled fusion reaction is magnetic confinement fusion. We'll devote a chapter for each one of them. In the case of inertial confinement fusion, the process in nature that we get inspiration from is the process of the formation of supernovae. A supernova is when a star collapses upon itself. The nuclei come in very close together. They overcome the Coulomb repulsion that we mentioned in the previous chapter, and the heavy elements are formed, the uranium and the thorium. This process of supernovae can also have an analog or a similar process of the collapse or the collision between neutron stars in general. So we're going to study the process, imitate the process by which the heavy nuclides are formed in trying to achieve fusion on Earth. The other process is the process of the capture of the charged particles from the solar wind in the Earth's magnetic field. And this is what we are going to call confinement, magnetic confinement fusion. There is progress in both approaches. We know that inertial confinement work in thermonuclear weapons, hydrogen bombs. Hydrogen in that case would be the isotopes of hydrogen, deuterium and tritium. The same fuel would be the one used in magnetic confinement fusion. There has been progress lately, and a new device is coming into operation at the center in Europe, in France, Cadarache, called ITER, the International Tokamak Fusion Experiment in that case. Last time we were looking at the fusion concept. We suggested that the fuel that we'd like to use on Earth are the deuterium and hydrogen as fuels extracted. Obviously, deuterium would be extracted from water, and tritium would be extracted from the reaction of neutrons with the isotopes of lithium, lithium-6 and lithium-7. If we start the fusion economy burning the easiest isotope, it would be deuterium plus tritium. But later on, deuterium is abundant in the water in our oceans, and it provides us with an unlimited energy supply. You can separate deuterium, as we learned in the chapter on isotopic separation, from water through distillation or through electrolysis, and it provides us with practical and unlimited energy supply. If you start fusing deuterium in a fusion plasma, you find yourself not just getting the two branches of the DD reaction here, the proton branch and the neutron branch, but the tritium produced here can immediately fuse with a deuteron through the DT reaction, producing a neutron and an alpha particle. And even the helium-3 from the neutron branch of the DD reaction would fuse with deuterium, and it becomes a D-helium-3 reaction. If you add all those reactions here, you find that we are really burning 6 deuterons, producing 2 protons, 2 alpha particles, and 2 neutrons. If you divide that into 2, you find that 1 deuteron is being turned into a proton, an alpha particle, and a neutron. 3 deuterons producing about 21.5 million electron volt of energy. The reaction D-helium-3 produces only charged particles. So if you can separate it from the process, you'll find that charged particles can be sent into a magnetic field. And in that case, you can get a nozzle. And this would be ideal for a reaction for a rocket. So in that case, you get a fusion rocket. It is the highest specific impulse that we can think about technologically. A trip to Mars using a very high impulse rocket using fission or fusion can shorten the time of the mission to weeks rather than years if we use only chemical rockets. So that D-helium-3 reaction is our way or our key to exploring the rest of the solar system for humans and maybe reach the rest of the stars. In the case that D-helium-3 reaction or the temperature of the plasma is not high enough, we get what we call the semi-catalyzed DD reaction, where we simply ignore the D-helium-3 reaction. This graph of the cross-sections shows that our first generation of fusion reactors would use the DT reaction. Obviously, you could see that it occurs, it reaches its highest cross-section or probability of interaction at a temperature of about 100 kilo electron volt. The D-helium-3 reaction needs higher temperatures. That means a higher experience with fusion systems that are run in a controlled fashion. This shows us the DDN, the neutron branch of the GD reaction, and this shows us a cross-section for the proton branch of the DD reaction. If you combine both of them, then you find that it needs a much higher temperature at a lower cross-section. So we need to gain the experience from DT reactions first, and then progress or evolve into DD reaction and maybe D-helium-3 reactions. For the first reaction to occur, we need to use neutrons to interact with lithium. Lithium is a metal, so we can use lithium as a liquid metal to cool the system, extract the energy, in fact, the kinetic energy from the GT reaction, if that's the first one that we're going to be using for the first fusion reactors. Those neutrons here carry 14 million electron volt of the 17.6 Q value of the reaction. Remember, it goes against intuition here. The lighter particle carries most of the kinetic energy as per conservation of momentum. All right, so in that case, lithium is going to be in our future a resource issue, because once we want to implement the DT fusion reaction, then the availability of lithium that we use today for lithium-ion batteries would become some kind of a resource problem. I gave you a list here of all the different fusion reactions that we can think of. You can have protons in a plasma with lithium to interact with each other. It's not just the GD proton branch, which is one that is an unlimited energy supply because of the deuteron presence in water, and the Earth is a water planet. 70% of the surface of the Earth is covered with waters. And we can even think about the helium-3 reaction, helium-3 plus helium-3. Helium-3 would be mined from the surface of the moon, in fact, because the solar wind impacts on the moon. And we know that there is a high proportion of helium-3 that is on the surface of the moon. All right, so we identified then two processes by which we would like, this is what we call the reaction fusion parameter, which is the average of the product of the microscopic cross-section with the speed of the ions. You could see that we need to heat the plasma, as we'll see pretty soon, as well as operate in an area where we have a high cross-section for the reaction itself. We describe different plasmas in terms of the power density, and the power density is proportional to that reaction parameter, the sigma the average of sigma V. All right, so we said then we are going to get inspiration from nature two processes offer themselves to us to try to imitate from nature. One that imitates what happens in a neutron star. And in that case, the name is given as inertial confinement fusion to the process, because it's a matter of a star, when a supernova occurs, it's a star that ran out of its fuel. The gravitational energy overcomes the expansion energy from the heat generated from the fusion reaction, and gravitational basically energy leads to an implosion or a collapse of the star, hence the name inertial confinement fusion. And it has its own applications. We know it works, again, in thermonuclear weapons. And in fact, there is a very important experiment in the United States, a whole facility called the National Ignition Facility at the Lawrence Livermore Lab that is exploring this idea. And the idea to generate the equivalent of a supernova has to be generated on Earth with some kind of a driver. So you can simply create this tiny little pellet, maybe made out of glass or plastic. Inside the pellet, you would enclose the fusion fuel, let's say a mixture of deuterium and tritium, and it would be deposited inside the sphere, soaking into the glass, and then in a cryogenic way cooled down, so it deposits itself on the inner surface of the sphere. The sphere would be the size of a grain of sand, as a matter of fact, or somehow slightly larger too. But in that case, you use an implosion process. So you get a number of laser beams or heavy ion beams or electron beams, and pin them on the surface of the sphere, evaporate the surface. So in that case, what you get is an inverse rocket. As that surface is evaporated, it moves outwards, and according to Newton's laws, then you find that that layer on the outside accelerates and implodes that pellet to a very, very, very small volume. As it implodes it, you find that the nuclei of the deuterium and tritium now are brought in close to each other. They overcome the Coulomb repulsion that we talked about in the last lecture, and they have a chance to fuse. The irradiation of the pellet with multiple beam, as shown here, can cause hydrodynamic instabilities, the Taylor instabilities. So in that case, one approach that comes in from the design of thermonuclear weapons is to uniformly irradiate the pellet by soft X-rays. So this is designated as a direct drive of laser beams, heavy ion beams, electron beams, or any kind of source of energy. In the indirect drive, you bring in laser beams from an opening of a plastic window here, a plastic window here, inside what is called the whole realm, a small enclosure made maybe out of gold. The laser beams hit the surface, the inner surface. They lose their energy, generate X-rays. So the whole volume here is now filled up with soft X-rays, and this is designated as a whole realm or black body radiator. Whole realm is a German name for it. And those X-rays now would irradiate that pellet uniformly, so you don't get the Rayleigh-Taylor instabilities that would result from creating fingers here of the material oozing out, the same as basically a liquid. And so this is what we designate as indirect drive. In the whole process, if you are really imitating what happens in a neutron star or in a supernova, to be more exact, the fusion energy occurs, the energy is released, and you'll find that the result now is that the results of the D plus T reaction or the D plus D reaction start expanding at high energy. You try to extract the energy from the products of those reactions, whether it's the neutrons in the DT reaction or the neutrons and the alpha particles in the DD reaction. The laser implosion process involves several steps here. You create an atmosphere by the irradiation of some external drive, a laser beam or a heavy ion beam or electron beam. You illuminate the target, you compress it, and we'll study that compression process. It's really similar to the implosion that is used in weapons, fission weapons, when they use plutonium, or some people even suggested using also uranium-235. So as you compress it using the implosion process, you can reach in the core a density 20 times the density of lead. And you know that lead has a density, actually it's the same as the density of silver, about 10 grams per cc. So if you get density that's 20 times the actual density of lead, that's 20, that becomes 200 grams per cc. At that level of compression, the nuclei overcome the Coulomb repulsion. The fusion fuel induces a reaction of fusion. That is what we call ignition, and then the burn propagates in the system. So that is an imitation of nature in terms of the neutron, in terms of supernovae. The other approach that we suggested that can be inspired by nature is the confinement of charged particles from the solar wind in the Earth's magnetic field in the Van Allen belts. The particles in that case are confined in the belt itself, and as they collide with each other for a long time. So here you have to keep them for a long enough time. We are going to call this the confinement time. In that case, they can fuse together using a magnetic field. So there are different configurations. The cylindrical one is called the tandem mirror. The one that's toroidal is either named the stellarator or the tokamak, and we'll study both of them. All right, so in that case, this process of generating fusion in a controlled fashion involves several processes. First, you start with a nuclei with nuclei of hydrogen, the deuterium or the tritium. Here we are showing a nucleus of just hydrogen, and you heat it. As you heat it, you ionize it. So in that case, ionization means that the electrons are separated from the nucleus. We know that the atom is neutral, so in that case, the nucleus becomes a positive ion, and the electrons are separated from it. That separated form of matter is what we call a plasma. A plasma has lots of electrons, so it is a state of matter like water or ice or steam, but in that case, it is a very highly heated kind of separated ions and electrons. And in that case, the ions are free to interact with each other. Notice that they're both positive, so they have to overcome the Coulomb repulsion. So either that you bring those nuclei very close to each other, or you maintain them in a container for a long enough time, like the Van Allen belts of the Earth, so that they can overcome the Coulomb repulsion and fuse together. In that case, we have to get back in a quantitative way, the Lorentz equation or the Joule's equation, like the French like to call it, which describes to us the force on a charged particle of charge Q in an electric field E as a vector and a magnetic field B as a vector. Here if you use, if you consider the charge motion in the electric field, it is subject to a force here as a vector that is in the same direction as the electric field. Let's ignore the electric field now and think about the magnetic field. You find that the charge of the particle is now multiplied in magnitude by the magnitude of the speed or the velocity here as a vector cross product into the magnetic field. And that V cross B product is perpendicular to both the velocity vector and to the magnetic field. This is from calculus, the cross product. That means that the particles are going to rotate around the magnetic field line, and that's what we use in imitation to what happens to the particles in the Earth, the solar hydrogen electrons from the solar wind in the Earth's magnetic field. That Q over C V cross B, C is the speed of light, is countered by the centrifugal force mv squared over r. So you'll find that the particles now rotate around the magnetic field line. If you take the magnitude of V and B, you get QVB is equal to CV squared over R. V and V cancel, and you find that the radius is what we call the gyro. Radius is equal to MVC divided into Q, the charge of the particle, and the strength of the magnetic field. You notice that the radius is proportional to the mass of the particle itself. All right, so we generated from a gas now, a deuterium gas, hydrogen gas, in fact, if you want to call it, we generated a plasma, and that plasma has to be contained in a container. Well, all right, so we generate the plasma inside the cylinder. Now, what will happen in that case is that the particles are moving in all directions. They will hit the walls of the container. If they don't get you a hole in the container, that has to be in a vacuum, obviously, since you want to have the deuterium and the tritium only inside the container. They lose their kinetic energy, and the plasma is cooled down, and the process of fusion will not occur. They have to keep their energy to overcome the Coulomb repulsion. So what do? Oh, we use that idea from the Lorentz equation that happens in our Earth, in our magnetic field on the Earth that traps the solar wind particles in the Van Allen belts, and we impose a magnetic field in the direction of that cylinder. In that case, the particles do not hit the wall. You don't have a big hole and you lose your vacuum in that case. And the particles now are rotating according to mv squared over r with their gyro radius inside the container, and have a better chance of first not hitting the wall and also hitting each other, and in that case causing fusion. The electrons obviously in the plasma are going to have a small radius according to our equation here. The electrons have a small mass, so their gyro radius or rotational radius is going to be smaller than the ions of, say, deuterium or tritium, and they move in opposite directions. The electron would move in one direction, the charged particles, the ions will move in the opposite direction. So in the same way as the Earth traps the solar wind particles in its radiation shields, the Van Allen belts here, a simple configuration of a cylinder can trap the particles in our own made magnetic field. Well, we still have a problem here, because as the charged particle rotate around the magnetic field lines, they'll rotate from this side, they'll escape from this side and this side. So what we want to do is also use inspiration from the Earth's magnetic field, in that near the poles, the magnetic field lines of the Earth, some kind of group together. The velocity vector of those charged particles would change, and we can create what we call a mirror. And this is the idea of the tandem mirror. In a moment, I'll show it to you. Or another easier thing to do is to take out that cylinder and connect both ends in the shape of a torus. So in that case, the particles follow the magnetic field lines and do not escape from the system. So in that case, it's shown here that you take that cylinder, you come in near the two ends and create a stronger magnetic field at that end of the cylinder and that end of the cylinder. And the right-hand rule says that if you circulate a current in that big coil, while it becomes a magnet, you find that you generate a magnetic field perpendicular to the coil. So you would what you would do is that you squeeze the magnetic field lines on both ends, and the particles would be confined in the center. This is what we call the tandem mirror configuration. Or As I suggested, you create a magnetic field by having currents circulate in coils, which are in fact, in that case, magnets surrounding a large torus configuration. And the particles in that case follow the magnetic field lines created by the magnets, as well as in fact their own the current created in the torus itself, and the two of them keep the particles confined, not touch first. They won't touch the wall and lose their kinetic energy and create a hole in the wall, and they'll keep being confined in the magnetic field lines. Either that you use magnets, and they'll have to be superconducting to reduce the amount of energy input. So superconducting coils in that case have to be designed and operated at cryogenic temperatures to reduce the energy loss that you would put in those magnets. Another approach is still to have a toroid, but instead of having magnets surrounding the toroid, have a large coil circulating around the toroid. In that case, you still create a magnetic field lines around which the particles are going to rotate and be confined in the system. And this is in essence, the approach for magnetic confinement fusion. So we have at our disposition here two approaches. One, to create the equivalent of a supernova by bringing the nuclei close to each other and compressing them or imploding them, inertial confinement fusion. Or we have the approach from nature of trapping the particles for as long as possible in maybe either a linear configuration with two mirrors at the end, two strong magnetic field here squeezing the magnetic field lines. In the case of the torus, we also have two possible configuration, one using magnets around the torus and one using just a coil circulating around the torus. This configuration here is designated as the tokamak, a name given by the Russians. We'll give it a whole chapter for our analysis. And in that configuration, that's a stellarator, as it is designated, invented in the United States at Princeton University. So this is the Russian approach. This is the American approach, if you want to call it. Lately, the emphasis has been on the tokamak. However, it has a problem, as I'll mention to you later in terms of technology, is that the center there is very confined. So maybe the stellarator would be used in our future operating reactors to produce fusion, because we have more space here in the center. Technology is going to interact with the science to achieve this type of a process. There is other processes that people have been thinking about other than creating magnetic confinement, which is a combination of the magnetic confinement and inertial confinement, trying to compress the plasma in a magnetic field. So in that case, there is a configuration that is named the dense plasma focus. So you apply a high voltage between an anode and an electrode. So in that case, you introduce also a part that is more or less an electrical component into the confinement process. And a dense plasma focus device has been built along this line. Okay, so suppose that we have confined the plasma in some configuration. Now we want to produce energy out of it. So in that case, we want to turn the fusion reaction into a power producing, and the best approach at that point is to produce electricity. So in that case, you need to turn the fusion process into a power plant. The first generation will use, of course, as I suggested, the DT reaction, because it is the easiest one to produce. It has the highest reactivity. So if you have a deuteron interacting with tritium, you get a neutron and an alpha particle. And the Q value, as we have seen before, is 17.6 million electron volt. And as I suggested, it goes against our intuition. The lighter particle, the neutron, carries 80% of the energy, 14.06 million electron volt, whereas the charged particle carries a smaller amount of energy, 3.54 million electron volt. Obviously, if you have that alpha particle here would deposit part of its energy in the plasma itself and part of it on the first wall of the device. The neutron, though, is penetrating. It can penetrate like a meter of concrete, as we know, and it carries 80% of the energy. So what do? We surround the plasma by some material that will slow down those neutrons. As they're slowed down by interacting with the material, they lose their kinetic energy. And here we have 80% of the energy of the DT reaction. The ideal material that people are thinking about is the metal lithium. As a liquid metal, neutrons will interact with lithium, lithium-6 and lithium-7. I showed you the reaction in that case, and that produces tritium for us for feeding back into the reactor from the lithium, what we call blanket in that case. Deuterium, it will come to us from the water in the ocean. So the first fusion reactors that we are going to build to produce fusion would have water from our oceans and tritium from our lithium. Luckily, we have large supplies existing on Earth of lithium. So in that case, this is the configuration of a possible nuclear fusion power plant. You create a fusion fuel of a plasma. You bring in your beams here, not shown, heavy ion beams or laser beams, and create the fusion reaction in the center. It could be magnetic confinement or inertial confinement. The DT reaction produces neutrons and alpha particles. The neutrons are slowed down in a lithium blanket, as we like to call it. Now, as the kinetic energy of the neutrons is deposited in the liquid metal, of course, it would be molten. So in that case, you circulate it, a hot fluid, take it to a heat exchanger, bring in any coolant, could be a gas like helium, or it could be water. And in that case, you take the water in the form of steam to a turbine, and you can produce electricity in that case. Not shown in the diagram is that now that lithium metal circulates, but now it has had an interaction with the neutrons, so it contains some tritium. So in that case, you separate the tritium from the metal and you use inject it back again with deuterium into the fusion plasma. So this is a way that is a conceptualization of how we produce electrical generation from fusion. What if we are using fusion for a rocket? These are the reactions with lithium-6 and lithium-7 producing the tritium because it doesn't exist on Earth, or it is a short half-life to isotopes. All right, so in that case, if we think about space propulsion, fusion will give us a rocket that has a because the fuel in that case is very light. Hydrogen is the lightest element. So the specific impulse, when we say specific, it's per unit mass. So the impulse, which is the integral of the force over time, divided by the mass of the fuel in a rocket. The fuel mass is very small, so that is called the specific impulse becomes very large, and you can get a large acceleration in the rocket. Compare in that case a Lamborghini automobile with 8 cylinders, maybe to a Volkswagen Bug with 4 cylinders. The reaction in that case that would be ideal is a deuterons plus helium-3 reaction, or another one of the reactions listed in the table that I've shown you earlier, like the P lithium-6 or P lithium-7. Let's say it's deuterium plus helium-3. How do you get helium-3? Well, some people suggested mining it from the surface of the moon. It is there from the solar wind. The gentleman who suggested that idea, Gerald Kolczynski, I worked with him. He was my teacher at the University of Wisconsin, Madison. And he suggested that every year, if we mine the surface of the moon, one space shuttle load can provide all the energy needs of the whole Earth. So that is in our future. Or if we produce tritium, remember that tritium decays into helium-3. And in that case, an electron is emitted without gamma rays. So if you produce tritium from a fusion reaction in a different reactor, then it decays into helium-3. The D plus helium-3 fusion reaction produces two charged particles, a proton and an alpha particle. And then now we can invoke the Lorentz equation again. If we burn that plasma and we get only charged particles, the charged particles can be confined in a magnetic field directed out of a magnetic nozzle, in that case, providing an impulse for the rocket to move in the opposite direction of the exhaust from the fusion nozzle. This suggestion is from the Lawrence Livermore National Lab of a microwave antenna heating the fuel, forming a plasma of D helium-3, and then it is directed out from a nozzle. And not to be outdone, the Russians came up with their own idea of how to get this to be working with inertial confinement in that case. So they are using an ellipsoid revolution, having two foci here, a focus here, and a focus here. And if you remember some of your geometry, any radiation emitted from that focus reflects off the wall of the ellipsoid of revolution into the other focus. So if you use laser beams here reflected from mirrors, you can generate a fusion reaction at that focus. The energy out of it would radiate, and with timing almost like an internal combustion engine, you would cause another fission at the other side of the focus. In that case, you create radiation here inside that big confinement part. The energy would be released from the bottom and your rocket would move forward. In that case, it is going to be, the choice would be the D helium-3 reaction. Now, let us talk again about that very interesting configuration of the ellipsoid of revolution. You are invited to find your way sometime, maybe on a Tuesday, because the entrance fee would be 0. You'll find lots of teachers taking their students from schools because the entrance fee is 0. And you go to the Museum of Science and Technology and Industry in Chicago and find your way to what's called the Whispering Gallery at the Museum of Science and Technology. This is a picture of that Whispering Gallery. You stand here. If you stand here at that podium, there is another podium on the other side. The shape of the Whispering Gallery takes the shape of that ellipsoid of revolution. If you whisper here, a person standing there on the other side can hear your whisper, just because of the radiation or the sound wave, in that case, reflecting off the walls of the Whispering Gallery. If you want to learn more about it, go to visit London, go to the St. John's Cathedral. The ceiling there has some kind of a form of that ellipsoid of revolution. If a person is standing here, you'll find that his voice reflects, and a person standing on the other side can hear his whisper. Some interesting application also comes in the I think the Senate building in the Capitol building in Washington, D.C., the Senate building suggests that they have a room designated as Statuary Hall. It has a parabolic reflecting ceiling, not ellipsoid of revolution. A tale exists that John Quincy Adams historically would sit at his desk situated at the focal point here of the ceiling, and then can hear the whispering of the other senators' conversations between unsuspecting subjects from different points around the room. So you could see the geometry here becomes an important part of the design of future inertial confinement fusion. I described to you here, if you design one of these devices, the geometry in the form of what's called in general geometrically the Cartesian oval, according to Fermat light theorem. The time that it takes to a ray to move from one focus of the wall and then to the other focus is a minimum. So you can, in that case, use that configuration here. I show the example to confine a particle. Here you could have emission of radiation. It will reflect itself off of the Cartesian oval. A special case of the Cartesian oval is what I named you earlier, the ellipsoid of revolution. In fact, that is a way or a part of the Ulam configuration to ignite a fusion plasma. So in that case, what you do is that you create a fission system here that generates radiation, X-rays out of the walls of an ellipsoid of revolution. It concentrates itself here at the point where you can ignite or start igniting the DT reaction. Go back to the Teller-Ulam configuration and see how that works in general. An interesting aspect of this type of research is the possibility that you can use fission to ignite fusion here, but you can also use really fission to ignite fusion at that point. So if the radiation comes out, reflects off the wall of the ellipsoid of revolution, you can implode a little uranium-235 pellet. The nuclei of the uranium will come very close together, they'll fission, and in that case, you can drive fusion out, you can drive fission out of fusion. It becomes, in that case, a hybrid of fusion-fission systems. So these are all ideas that scientists are looking at. The hybrid, in that case, uses to advantage the properties of fission and fusion in an optimal manner. We know that fusion has a very high energy in its neutrons, so it's neutron rich. The DT reaction produces a neutron with 14.06 million electron volt, whereas fission is neutron poor. A fission neutron is only 2 million electron volts. However, fission, being neutron poor, is also energy rich. A single fission reaction produces 200 million electron volt, whereas a fusion reaction between, say, deuterium and tritium produces 17.6 million electron volt. So fusion is neutron rich but energy poor, and fission is neutron poor but energy rich. So in that case, an optimal combination would be a combination of fusion and fission, and in that case, we call it a hybrid. The potential advantage of this approach in our future as compared to a critical fast reactors are that you get a higher flexibility regarding the form of the actinide fuel and the coolant. You can attain maximum net burning of the actinides, and you can have even enhanced safety characteristics of the system. The technical demands on a DT fusion plasma neutron source are lower by more than an order of magnitude compared to those of a pure fusion system. This reduction in technical demands is thought to lead to lower costs and feasibility for a fusion-fission hybrid as compared to pure fusion or a pure fission system. The topic of hybrids may also be the first way that we can obtain fusion, because you get an energy magnification or in the system, in that case by a factor of 10. And we'll see later that we are a factor of 10 away from attaining a self-sustained fusion, pure fusion reaction. So maybe a hybrid would be our way to fusion. I'll stop at that chapter here and go to the chat room. If you have any questions, I'll be happy to answer. Okay, there are some comments in the chat room. I think you accidentally muted my audio. Is it functioning now? Okay, so that has been fixed. All right, so we really had a nice review now of what we think we need to share the screen back again. How can we achieve fusion? That's a dream of all of humanity in that case. So we go back and let's see here. in sharing, and I hope we are recording. We have to start thinking about inertial confinement fusion and magnetic confinement fusion in that case. Let us start with one that has some interest in terms of the mathematical treatment here, which is inertial confinement fusion. And we know it happens. It happens when we get supernovae. We observe it when stars collapse upon themselves. In fact, all our Earth, in terms of being a rocky planet, has been formed, to our best knowledge, in one of those cataclysms in the past, 4.6 billion years ago, when a star collapsed upon itself, forming our Earth. And this is an interesting, again, the comparison in terms of the actual pictures here. This is a picture of a supernova, type 1a supernova happening that happened in 1987. And look here, this is a picture of an experimental inertial confinement pellet, 500 picoseconds from ignition. So you could see here that we're really trying to imitate in the ignition of a fusion inertial confinement pellet what happens in the stars. That's another NASA picture of two supernovae occurring at the same, almost at the same time in the same galaxy in that case. So let us look again at the confinement method. As I suggested, we have two approaches: the direct laser drive. So you get maybe 12 laser beams or 12 ion beams or electron beams, irradiate the surface of a small pellet containing the fusion fuel here, deuterium plus tritium or deuterium plus deuterium. You evaporate the surface. As you evaporate it, the gases move out. As they move out, you create an inverse rocket, create basically an implosion process that compresses the pellet, brings all the nuclei very close to each other. They overcome the Coulomb repulsion, they fuse, and then the energy is released with the pellet expanding. Now, what you started with as deuterium and tritium becomes an alpha particle plus a neutron. And then you put it into the power production process, as I've shown a little while ago. So this is what we call the direct drive. As I suggested, we get into a problem here is that of the Rayleigh-Taylor instability. It's a hydrodynamic instability that you can run an experiment of your own at home. Just get a cup, fill it with water, and then add oil very slowly. Actually, add oil first in the cup at the bottom, then add water on top of it very slowly. So initially, you'll find that the water stays on top of the oil. But you know that the oil density is lower than the water density. So if you give basically a little tap on the cup, you'll find that the oil now starts moving up through the water in the form of little fingers, and the oil finds its way to the top as now, because it has a lower density, it floats on the top. When you irradiate that surface of the fuel here, you can get those fingers. They're called fingers of instability in that case, and the irradiation is not uniform. So we want to make that irradiation uniform, and that's one of the secrets on how hydrogen devices are built. You use, in that case, soft X-rays. So in that case, you get a different configuration, and that's what we call the whole round concept. So here you get a little maybe container. I'll show you an actual picture of an actual container. You'll find that you can have a window on the top and the bottom, plastic window maybe. The laser beams come in and hit the surface of the container. They lose their energy in the form of X-rays. So the full container now is filled up with X-rays, soft X-rays. They do not penetrate into the pellet, but they irradiate the surface in a uniform way. And that's why it's called an indirect drive. The whole round, the name, the German name for the German language name for the black body radiator and using soft X-rays. That's one of the secrets of the nuclear age, really, in the generation of fusion in hydrogen bombs, the use of soft X-rays rather than the direct configuration in general. The same steps as direct radiation happens, but we don't get those hydrodynamic instabilities, and we can achieve it through a compression process. All right, so you can also, some people are doing research on the use of a single beam rather than using multiple beams and or soft X-rays. What they do is that first they generate an atmosphere around the pellet using the inverse rocket concept, and then they follow it with a single beam hitting now that formed atmosphere, and in that case you get an asymmetric compression of the pellet. So this is under experimentation, yet it's not really highly adopted. In any case, what we are using here is what we are going to call an implosion process. So let us learn the mathematics. It involves simply applying the laws of conservation of mass from fluid mechanics. And so let us consider, for instance, that if you had a little cylinder and you irradiate that cylinder from both sides, in that case, it is named linear compression. From fluid mechanics, one of the laws of fluid mechanics is that mass is conserved. So if you have a small volume of a cylinder with a density initially rho sub 0, and you compress it from both sides with two beams from either side, you'll find that the density now is going to increase to rho and multiplied by the volume. And that mass here before compression should be equal to the mass after compression, conservation of mass. All right, now what is the volume? The volume is the area of that cylinder multiplied by the length part of the cylinder that is irradiated, and that should be equal to the A before compression by the length of the cylinder. The area and the area cancel out, so you end up with that the product of the initial radius by the initial density is equal now to the new density multiplied into the radius. If we simply rearrange the equation, you find that your initial density becomes the new density becomes the initial density multiplied by the ratio of the radii. And we suggested that in that case, in some inertial confinement pellets, we can reach 20 times the density of lead. So in that case, that ratio here could be 20 times, maybe if you are using lead or you're using uranium even, about 20 times the level of compression. It suggests that the compressed density is inversely proportional to the change in scale or the relative change in length. And this is a process if you do the compression in a linear fashion. Now, suppose that we become a little more inventive and try to do that compression in a cylindrical fashion. So in that case, the law of conservation of mass from fluid mechanics still applies. The mass before compression, which is the density multiplied by the initial volume, should be equal to the mass after compression multiplied into the new volume. Now, if we are using a cylinder and compressing the cylinder from its sides, not from both of its ends, like in the linear compression, you'll find that the area of the cylinder, now that you are the length of the cylinder multiplied by pi r sub 0 squared, this is the area of the cross-sectional area of the cylinder, should be equal to the length of the cylinder multiplied by the new cross-sectional area multiplied into the density. L pi and L pi cancel out, and we get something very interesting here, that here now you find that the new density rho sub rho is equal to the initial density multiplied by the compression ratio. Let's call it the compression ratio because we have now increased the radius r sub 0 by a factor of, say, 10 or maybe even, who knows, 20 or 100. So in that case, notice here now that if you change the geometry from a linear compression, the compression ratio being the initial radius divided into the new radius, say a factor of 2 or 10, here you get that R naught over R squared just by changing the geometry. And that implies that, oh, okay, what happens now in cylindrical, in spherical geometry? So in that case, you take a sphere, conservation of mass again from fluid mechanics applies. Now you take the initial volume of the sphere, 4/3 pi r sub 0 cubed, the initial density, it becomes a new density after you compress it, 4/3 of pi cancel from both sides. And look here, something very interesting happens is that your new density rho becomes the initial density r sub 0, but then the compression ratio is to the cube power, not just to this to the second power, like in the case of cylindrical compression, or the power of 1 in the case of linear compression. So you could see here now that the new density is proportional to the cube of the change in scale. And that's why in the diagrams that I have shown you for pellets for inertial confinement fusion, we definitely would like to use spherical compression, because the compression rate, depending on the geometry, how much you reduce the radius, your density can be increased by the cube of the compression ratio. Notice also that it depends on the product rho r. The density multiplies into r, and this is a figure of merit used in the design of those fusion pellets. In general, the new density under implosion is equal to the initial density multiplied into the initial radius divided into the r, that is the new ratio, and n here would be the compression dimension. In spherical geometry, it's 3. In cylindrical geometry, it's 2, and in linear geometry is 1. So obviously, you would like to use compression, spherical geometry if you are doing an implosion process. And that applies to both fusion here in inertial confinement fusion, very simple application of the laws of fluid mechanics. And it applies also, by the way, to the implosion of a fission weapon. Like if you use plutonium, the density initially, if you use the compression this way, you bring the nuclei together, and your critical mass would be much smaller if you compress the field. So implosion is used in fission devices, and it will be used in inertial confinement fusion in the future. So let's take an example here, a numerical example, to see how just the geometry affects the process of implosion. And we know in nature, that's what happens. It's a spherical kind of an implosion of the supernova. And in the case of inertial confinement fusion, it will be also the same. So let us take N3. This means that we are using spherical compression. Let us assume that we are able, with laser beams or using soft X-rays, to reduce the initial ratio R sub 0 by a factor of 2. So we simply reduced, brought the nuclei radially to half the initial radius. So R naught over R becomes 2, and N in spherical geometry is 3. So if you start with the density R sub 0 of a compression ratio of 2, you find that 2 to the 3rd power is 8, and you find yourself getting 8 times the initial density. Suppose that you have better technology and you can reduce that radius by a factor of 10. Well, now in that case, the new density becomes the old density multiplied into the compression ratio of 10. Oh, 10 to the 3rd power is 1,000. So in that case, you can increase the density by a factor of 1,000 if you can reach that compression ratio of 1/10 the initial ratio. So you could see for the same change in scale, a higher dimension and implosion produces a much greater degree of compression. Just by using the laws of fluid mechanics, the inefficient linear case, in fact, is rarely thought of as being an implosion process. Obviously, the spherical implosion gives the most rapid compression, and being symmetrical in all direction, it is also easier to analyze theoretically. We don't need really a supercomputer to figure out how much is the compression ratio like what we are doing here. An interesting aspect of it is that you also can have a hybrid in that case, in the sense that you can have a little tiny piece of fissile material, and you can use laser beams to bring that very tiny amount into very high density and cause it to fission in combination with fusion. So a hybrid could be our way of reaching fusion in a shorter period of time. And here now we go and having done the theory here, I'll give you a problem on the implosion process to convince yourself that you can really increase the density through the implosion process. And that's what happens in nature in a supernovae. In the lab, this is what is being done. Now we have ingenious designs of the pellets studying the process. This is a laser pellet. It's really a gas bag design, which it has two tubes, as you could see here, that brings in the fusion gas into the pellet. So now it's filled with deuterium and tritium. Then you cool it, you turn the gas on the inside into a layer of ice on the inside of the pellet. You add that kind of a wing, like the Saturn wings, out maybe of some material that would absorb the laser beams. You create here a gas atmosphere that acts as it expands as an inverse rocket and compresses the pellet in the center. So, and these are the filling tubes. So these are experiments on generating this cylindrical, spherical fusion. As I suggested, more experiments are going into the indirect type of fusion. So you could see here now is cylinder. It's really what we call the whole round, attached to the tip of a glass rod. It has a window here, a window here. You could see if you look from both ends that you have a window where we introduce, in that case, laser beams from the window hitting the walls, not the pellet, just the walls. X-rays are generated inside what we call the whole round or the black body radiator. And the pellet now, it has to be soft X-rays, because if you use hard X-rays or high energy X-rays, they'll penetrate into the pellet. What you need is soft X-rays that only will heat and evaporate the surface of the rocket, and the expansion of the gas in that case would create that inverse rocket action. This is an actual experimental device here. It looks like a wagon wheel. This is made out of gold experimentally. Obviously, in a future reactor, we cannot use gold, too expensive. You levitate a pellet at the center in some kind of polystyrene like foam sphere. You irradiate the pellet, the walls from both sides with laser beams. The X-rays would implode the pellet in the center. These are experimental, basically experiments in the lab about it. And this is a detailed design of one of those pellets. If you could see it here, let me show it in a whole diagram. You would have multiple beams, laser beams hitting the walls of the whole round. The window here at the top and the bottom is a 1 micrometer thick polyimide window plastic. In fact, you get a cooling ring here so that you can generate cryogenic temperatures, and you fill the whole round with helium plus hydrogen fill, about 1 milligram per cubic centimeter. The pellet would be in the center, levitated in the center by those two wings right here. The cryogenic fuel would be deuterium and tritium cooled. So if you cool the gas inside the pellet, obviously it deposits itself as a shell of the deuterium and tritium. So this would be a solid DT, deuterium plus tritium fuel layer thickness, about 80 micrometers. So it's really nanotechnology in that case. And the laser beams come in from both windows. And this is very small, that's 5.5 millimeters. So that is half a centimeter in size. So you could see that it's nanotechnology in that case. This is now laser beams coming in from the windows of one of those hole rounds. They have been set to hit the walls. They deposit their energy on the wall, not on the pellet itself, inside the metal cylinder or hole round, and that's the X-rays, which was the secret really of how to implode the fusion part of a thermonuclear device or a hydrogen bomb. This is an actual X-ray photograph on a laser that I'll show you in a moment, to the NOVA laser. In that case, you could see that the laser beams are hitting the walls inside the hole round. That's a glass rod holding that half a centimeter in size diameter pellet in general. Some people talk about a dynamic hole round. So in that case, this is an X-ray of a dynamic hole round. So you shape the radiation from the X-rays. To maximize the process of implosion, we can use the concept of a hammer hitting an anvil. In that case, you can even increase in the density. So here is a pellet design in the lab on top of a small rod here, as you could see. But then you have the pellet here, and on the outside, you have another layer of material, and you evaporate the outer layer, so you accelerate it to hit the inner part. So in that case, it acts like a hammer hitting an anvil, and the pellet would be levitated at the center of a double shell hammer and anvil target. So in that case, it's not just a mass conservation in imploding the pellet, but also momentum conservation. If you take the momentum of the outer shell being transferred to the inner shell, and then you can attain hopefully much higher densities in the compression process in general. To levitate the pellet inside the target, you have to use something that has a very low density. Foam has been used, but some people even use what's called an aerogel. An aerogel has a density that's less than air. It would float in the air if you let it release it. You find here the density 15 milligram per centimeter cube. The size is the nanotechnology size 1 to 10 micrometers. The chemical composition is very simple. CH, carbon and hydrogen. It's plastic. Some of them is silicon oxide, but CH2 really, these are plastic, divinyl benzene or polyformethyl 1-pentene. And the name for it is resorcicol formaldehyde aerogel, or simple polystyrene. Polystyrene is what you use in packaging as foam. So in that case, that is what's used to levitate the pellet in the center of the hole round itself. Material choices. Right now, I've shown you pellets that use gold and gadolinium, but for future reactor type of pellets, you cannot use gold. It's a precious metal, but some people have suggested the use of lead or mercury or lead and hafnium as a material. Of course, they have to be recycled. All right, so we talked here about the design of the pellets itself, but what are the drivers to the energy, delivering the energy to the pellets? Every national laboratory in the United States has one or two of their favorite ways in experimenting on how to achieve that inertial confinement fusion. And some of you, even if you are a mechanical or electrical engineer, may find yourself involved some way or the other. Actually, one of our deans in the College of Engineering was involved and he was very proud of working on those heavy iron beams, but for the tokamaks, not for the inertial confinement. If you go to the Lawrence Berkeley National Laboratory, I'll show you a picture of it. They use heavy ions. So you accelerate heavy ions of neon, maybe, or xenon to irradiate the pellets. The Lawrence Livermore lab also, that's not the Berkeley, but the Lawrence Livermore lab use solid state neodymium laser. So that's their favorite is lasers. The United States Naval Research Laboratory preferred driver is krypton fluoride lasers. If you go to Sandia National Laboratory, it's a Z-pinch. It generates X-rays. And this one has a very interesting application is that the corona discharges in the Z-pinch are really the picture that we see in the movie, the Matrix. In that case, I'll try to remember that. The University of Rochester uses laser capsule irradiation. A company in the area of San Diego, General Atomics, fabricates actually those fabrication. Also, light ions and even electron beams are also under consideration. So you carry the energy to the surface of the pellet using many different drivers. Those drivers that I mentioned are shown here. Just to give you an idea about the size, look at that engineer or scientist working there on a heavy ion 4-beam accelerator. This is at the Berkeley National Laboratory. And this is what's called the National Ignition Facility. It is shown here under construction. It has been constructed. You could see it's a very large facility there. It is being used for both the civilian research on how to achieve inertial confinement fusion. It's a place maybe that you'd like to interview to join in the effort, but it's also a way of the stewardship of the nuclear thermonuclear weapon stockpile of the United States. The Russians have a similar configuration, the French, the British. Of course, you know that testing nuclear weapons is banned. A very good idea, but maintaining a safe stockpile that doesn't say go and explode by itself needs that you have to simulate, in that case on computers and experiments, what happened in thermonuclear weapons. But it is a dual purpose here, hopefully from that research on the stewardship of the weapons that we can get an application, a spin-off into civilian use. Like in the space program, the use of fuel cells by NASA now is considered for a modern electrical vehicle configuration. It's a huge facility, as you could see here, and experiments really concentrate, and they are making progress in the fusion ignition itself. This is the Naval National Laboratory, just to give you an idea about the sizes. Notice that gentleman or lady here on a computer, and this is a spherical chamber where the laser, the krypton fluoride laser comes in. This is a picture of the Z-pinch facility that uses electron beams at the Sandia National Laboratory. And look here, the corona discharge shape is really what they took in the Matrix movie to show some special effects in the movie. Maybe here it is more shown here. This is the corona discharge of the electrical discharges in the water along the beam lines, very reminiscent of the Matrix movie. I think going to a light ion, you can use also light ions like xenon ions and so on. That would be both at the Los Alamos National Laboratory, the Trident system at the Los Alamos National Laboratory. So the research in the drivers, of course, goes across all the engineering disciplines, because that's partly mechanical, partly electrical, partly nuclear, and so on. The main facility in terms of inertial confinement fusion, that since this is a topic of our chapter, is the National Ignition Facility. And here we go back to an actual target now. I've shown you a diagram of how what the components of the target, but this is a picture of an actual whole round target. This is what they use at the National Ignition Facility. You could see they're using a gold whole round with a window made out of those plastics for the laser beams to come in, irradiate the surface, and the pellet being levitated in the center. So, and this is all 0.5 centimeter, 0.55 millimeter in 5 millimeter in size, half a centimeter in shape. So this is a marvel in nanotechnology. This was the ignition facility is an evolution of what was originally named the NOVA target chamber. You could see the spherical chamber right here with an engineer here getting some adjustments, and here and here and here. These are mirrors from the laser beams. That one uses lasers coming it to the center of the chamber. And if you get into the center of the chamber, this is the way it would look like. Notice here that the engineer or scientist here on some kind of a bucket inside the large chamber. That is at the National Ignition Facility. And this is the beams coming in. And this is what keeps the pellet at the center where the beams come and irradiate the pellet. So in that case, here is another picture of the target chamber from the outside of the NOVA laser. Again, you could see here those two gentlemen to give you an idea about the size, quite large in size here. And those are laser beams coming in reflected from mirrors, and the laser beams are produced obviously in those very long cylinder, which makes the size of that ignition facility quite large. Look at that gentleman here in the center. When we show those people in the pictures, it gives us an idea about the size. So these are laser beam sizes. This is a marvel in technology, and because if you have a pellet here at the center and you fuse deuterium plus tritium, you get neutrons emitted, and those neutrons now could hit the mirrors and damage them. And those mirrors are really very highly polished materials like beryllium, and you don't want your neutrons out of the implosion itself to reach the main amplifier here, the electronics of the system. So you can see here that you get multiple reflections of the mirrors. If you look to, there is a report that I have contributed to, actually designed it, that end mirror, as we call it. You have to make it out of a metal like beryllium maybe, so that it can sustain the damage from the neutrons. So you get 9-degree angles, so that the neutrons deposit their energy in the metal here and do not move down the line to the main amplifier. So you have a power amplifier and optical switch. It's a marvel of laser technology. So our electrical engineers are involved in that job. There are hurdles to be surmounted, and we need to describe it in a quantitative way. And the way to describe really when and if and how we can reach that fusion energy is described with what we call the Lawson criterion. Lawson was a British engineer, and he figured out that to achieve a fusion process, you have to invest in energy. And the energy investment would be in the energy that you have to give your maybe drivers, the laser beams. Now, the fusion process is going to produce energy output. So he took the ratio of the energy output to the energy input and was able to get some kind of a criterion of what is needed to achieve a fusion process. And he came up with that very simple description of the criterion to reach fusion. And people call it the Lawson parameter or the Lawson criterion, and you need to know what it is. So I'll give you an assignment in describing it. And it is described in the product of 3 parameters. One of them is the ion density in ions in the whatever plasma you are creating to achieve fusion. And obviously in inertial confinement fusion, you want to keep that N sub I as high as possible. This is the purpose of the implosion process. But you also need to keep a very high temperature for that plasma. So that's described with a Kelvin's temperature, or in kilo electron volt. This is the ion energy of the plasma. So in that case, you have to maintain a high density, a high temperature, but also a high energy confinement time. This is a time over which the ions in the plasma are in contact with each other. And the product of these three quantities have to be larger or equal to 10 to the 20 to get a net production in energy. And producing energy, as we all know, needs an investment in energy. Even in conventional fuels, to get petroleum, you have to explore for petroleum, you spend energy. You have to drill for petroleum, you spend energy. You have to refine the petroleum, you spend energy. You have to distribute it to the gas stations, you spend energy. But then when you put the petroleum in your engine, you get more energy than the energy that you invested in producing and marketing it. In the same way, in any energy device, the energy output should be larger or equal to the energy input. So in that case, applying this idea that the energy output should be larger or equal than the energy input, the product of the density multiplied by the energy confinement time by the temperature of the plasma should be larger or equal to 10 to the 20th ion. The unit would be ions per meter cubed, the SI system of units for N sub I. Tau sub E would be in seconds, the confinement time. And the temperature here is, or energy of the plasma, described in kilo electron volt. When you have the equal sign, then the energy in is equal to the energy out. And we call that the break-even point, meaning that your investment in energy to produce an energy output, the investment in energy is equal to just the energy output. Obviously, you want that number to be as large as possible if you want to have a meaningful type of energy producing system. And it doesn't make sense to have energy put into a plasma, produce energy, but it would be, the produced energy would be less than the invested energy in creating the plasma and the laser beams or the heavy ion beam. So the Lawson criterion or the Lawson parameter is a figure of merit that tells us how we are really approaching the process of controlled fusion on Earth. And this is a way of using our resources on Earth for our technological civilization to reach the level 1 when we use all our resources of energy on Earth according to the Kardashev scale, if you go back to our first lecture. Notice here that the progress started being in fusion started in the 1960s. If you look at the time scale here, you'll find that if you plot the Lawson parameter, N sub I, the ion density, tau sub E, the energy confinement time, multiplied into T sub I, the plasma energy, is that over time, on a logarithmic scale, we are getting closer and closer to that break-even point where that equal sign now applies, that N sub I, tau sub E, T sub I is equal to 10 to the 20th. This is a break-even point. We haven't reached that point yet. When we go beyond that point, which is a Lawson parameter of about 10 to 100, then, oh yeah, we have now ignition, meaning that we are getting more energy out than energy into from our plasma. And in that case, we would have achieved the burning plasma. We haven't reached that point yet. And notice here that the fuel used in those experiments is deuterium plus deuterium, the DD fusion reaction, as you could see most of them here. But some experiments basically tried also to use DT. They used deuterium plus deuterium to avoid the formation of radioactivity products in the walls and the instrumentation from the 14 million electron volt neutrons. So that's the Lawson criterion approaching ignition. Ignition is hoped to be attained by that NIF that we mentioned a few moments ago, which is the National Ignition Facility. That would be through inertial confinement fusion. And through magnetic confinement fusion, there is another experiment, the International Tokamak Experimental Reactor, that has really been put together. It's ready for operation in France. So the two approaches used are the the inertial confinement, like in today's chapter, and the magnetic confinement represented by the international tokamak reactor. So we are headed there, but we are not there yet. Along this line, I'd like to introduce you to the idea again of the hybrid. The hybrid, as I suggested, is an optimal combination of fission and fusion. People in the fusion field resist the idea of using the hybrid. Yet notice here that we are a factor of 10 only close above to attain break even. You are still below break even. And I suggested that if you get a combination of fusion and fission, then you can get that I'm sorry, with a factor of 10 amplification in the Lawson criterion, you can get fusion in our lifetimes. And I don't know, the phone rang and something appeared on the screen here. But let's go and look at the concept of the hybrid. The hybrid would give us that factor of 10 that we are still away from achieving the break-even condition. And in that case, you could think about maybe a configuration that looks like a spiral where you can have a fission pellet here driven by a fusion beam. And in that case, we have a combination of fission and fusion. I show you the mechanics of and the geometry application in that case. It is not the same as the ellipsoid of revolution that I described earlier, but I don't think you need to worry about the mathematics in that case. So our exercise for today in the assignment is to figure out for yourself some numbers. If you use metallic uranium in a hybrid and you implode it by a fusion device, can you achieve criticality? And if you can implode, say, fission uranium to 1/2 its initial radius or 1/10 its initial radius, you could see that you can increase the density tremendously and inertial confinement fusion is achieved. All right, again, I am back in the chat room for any questions. Let me see here. If no questions, I'll keep going and into starting on magnetic confinement fusion. All right, so in that case, we go back to our sharing the screen and we don't waste time. The other approach of fusion is what we call magnetic confinement fusion. So let's start talking about the other approach to fusion that is under consideration, which is magnetic confinement fusion. In magnetic confinement fusion, let me see here. What we want is to amplify the plasma. Now, if we go back also to the Lawson criterion, we have a product of n sub I, increasing the ion density, and that's what compressing the pellet of fusion material can achieve. But if you want to operate with lower densities, then you have to increase the energy confinement time. So you have to keep that tau sub E in the Lawson criterion and make it as large as possible. In essence, then, in the Lawson criterion, what we want to do is get thermonuclear power generation larger than the input that we put into generating the laser beams or the heavy ion beams relative. That would be the power in the input part of the device. And this is described in what we call the amplification factor of the plasma, Q. So the Q is simply the ratio of the thermonuclear power divided into the input power. And in the same way that we talked about the Lawson criterion earlier, then that ratio obviously must be larger than unity. Otherwise, it makes no sense to create a system where you put in energy that you don't get out. Let us expand a little bit on the Lawson criterion and of the Lawson parameter. Let's look first about the temperature of the plasma. The temperature of the plasma is represented by kT, which is the energy that you impart to the ions that are taking part in the fusion reaction. And if we take it in Kelvin degrees rather than kilo electron volt, here we are talking about 100 million kelvins. And the Kelvin is basically 273 plus degrees Celsius. So this is temperatures at the same level as a corona that is surrounding our sun. That has to be a very high temperature plasma. If we talked about the part of the energy confinement time, you want confinement time in magnetic confinement that is larger or equal to 2 seconds. Now remember that in the Lawson criterion equation, that energy confinement time is multiplied by the ion density. So if you achieve a very high ion density, you can afford to go for a short energy confinement time. That's inertial confinement. But if you cannot achieve a very high density and you want to maintain your particles trapped in a magnetic field, then you need your energy confinement time to be as high as possible. So hence the configuration of the magnetic field has to be as to trap the particles in the magnetic field. So going back to the plasma density, we need a plasma density in the range of 10 to the 14 particles per centimeter cube. This is 250,000 times less than the density in the Earth's atmosphere. So it's almost a vacuum. This extremely low density means that despite its high temperature, here is the million degrees Kelvin, 100 million kelvins. You can also operate a burning plasma involves a power density scarcely larger than an ordinary light bulb. That's what is inside an experiment, say, of tokamak or a stellarator. So it's not an energy that is going to cause a fire, for instance. And that energy break even, as I suggested, according to the Lawson criterion or the Lawson parameter, we need that parameter to be larger than 10 to the 20s if we use the form where we have the ion density multiplied by the energy confinement time multiplied by the energy of the plasma. If you ignore the temperature, the product of the density by the energy confinement time must be larger or equal to 10 to the 14th particles second per centimeter cube. The density is particles per centimeter cube, and the energy confinement time is seconds. So in the case of magnetic confinement, I'm showing that equation here, ignoring the temperature, because we need high temperature anyway. We emphasize the energy confinement time. We want to maintain the plasma for as long as possible so that the nuclei can fuse together. And in that case, we can operate with low density plasmas. As I suggested, the vacuum is the same as what you would have in a light bulb in the case of magnetic confinement. In the same way that in inertial confinement, we deal with the configurations or the geometry, you'll find that the geometry is an important factor in the case of magnetic confinement. We can confine a plasma in a shape of a cylinder. And in that case, we suggested that at the ends of the cylinder, you create a magnetic mirror, with the mirror ratio being the ratio of the magnetic field generated by the magnetic field at the mirror divided by the magnetic field in the linear part of the device. A device that uses the linear kind of magnetic confinement is what we call the tandem mirror. So it's a long cylinder. One half of it is shown here, surrounded by coils in which you circulate a current. If you circulate a current in a circular fashion in that coil, you create a magnetic field in the direction of your thumb if the direction of rotation of the current in the coils or the magnets in that case, because that becomes a magnet, is in the direction of your fingers. The particles would leak from the ends on both ends, but if you bring in a larger magnet near the ends. You bring the magnetic field line, you squeeze them, literally squeeze them together. So in that case, a particle moving around the magnetic field lines find itself reversing its direction vector and reflects back into the mirror. Some of it will still leak. Some of the particles will leak from both ends. So it becomes a technological challenge to design those end mirrors in the what we call the tandem mirror device. So people have been trying to find those plasmas in the tandem mirror. For instance, they use the yin-yang coils here near the end, and you can find a report at least about how to design one of those in the portal to the class. Some people try to use a field reverse configuration. They take one of the two of the magnets, and they simply generate a magnetic field and reverse it, and that's called the field reverse configuration. You create some magnetic field that's in the form of a torus. Think about rotations this way. So that further squeezes the magnetic mean lines of the tandem mirror and keeps the particle in the center. So this is what's called the tandem mirror. You find that you also have to design that end plug with a combination of electrostatic fields and magnetic field. So you can have a double hump in terms of the magnetic field, but in the center you also create an electrostatic field, and that would confine the particle in the plasma in the cylindrical lengths in the center. So in that case, you get a central solenoid plasma region. It can be 100 meters in length. Could be a very large device in that case. And the mirror pair and cell would have a combination of electrostatic fields and magnetic fields. So the design of those mirrors is basically an engineering challenge. This is a picture of an actual device, the tandem mirror experiment, TMX device, at the Lawrence Livermore National Laboratory. You could see that scientists working here. Look here, these are the end parts of the tandem mirror. It's a very short tandem mirror, but the mirrors at both ends are really the main design feature in there that they are have to consider in operating such a system. Now, another system that I suggested is that instead of having a long cylinder like in the tandem mirror, how about closing both ends of that cylindrical mirror in the form of a torus? And that is in fact what the Russians have done. The idea was introduced by a famous Russian scientist. His name was Basov. Mr. Basov visited us here in Champaign-Urbana on an event hosted by the IEEE Plasma Physics Division. I took part in it with Professor George Miley, if you have met him, and he visited us here, and he is the one who invented this idea of the what we call the tokamak. One of the early tokamaks is what's called the T15 design, built by Mr. Basov at the Kurchatov Institute in Moscow. And you could see here that it has a cylindric, a toroidal kind of shape. And these are big, leafed kind of steel layers. This is a transformer, because the tokamak actually, or the T15 device shown here, is really a big monster transformer where you get the energy into the plasma from transformer action. So in a transformer, you know that you would have coils surrounding the primary part of the transformer, and the secondary part of the transformer gets the current through the magnetic field lines created in the magnetic part of the transformer. In that case, the plasma itself becomes the secondary part of the transformer itself. So you add energy to the plasma and create the plasma by transformer action, where the energy in the magnetic field of the coils is transferred to the plasma itself. Remember, the plasma is a combination of positive and negative ions, so it's a conducting medium, and it acts as a secondary of the transformer. So in that case, a tokamak is composed of different components. One of them is what we are going to call the toroidal field. To create a toroidal field, you use magnets or coils that surround the plasma. The plasma itself has a current moving in it. So in that case, a current moving in a wire. In that case, the plasma has an electric field rotating around it. We call this the poloidal field. I'll show you the configuration in a moment. To keep the plasma in the toroidal geometry, because the magnetic field would be larger near the inner part of the torus than the outer part, you have to cancel that vertical field. We have to also add coils to cancel that vertical field coins. And this is the configuration in the end that we get for a tokamak. As I said, it's a giant transformer. The plasma would be confined in the toroidal region right here. The plasma current itself generates its own magnetic field surrounding the plasma. So we call this the colloidal magnetic field. So if the current in the plasma is moving in this direction, if you apply the right-hand rule, you'll find that you get a magnetic field surrounding the plasma right here. But then that field itself is not sufficient to keep the particles from touching the walls. If they touch the wall, they lose their energy. We want to keep that energy high, or you can have a hole in the vacuum of the plasma. So in that case, you use the current, the plasma itself, as a secondary of a large transformer, the iron transformer core. These are what's shown here in the diagram of the T15 tokamak design. And let's go back here, down here again. And you find that now you have a current going in the primary of the transformer, but instead of having other wires as the secondary of the transformer, the plasma itself acts as the secondary. So in that case, you heat the plasma by transferring energy from the winding of the primary of the transformer, as well as now, and that creates a plasma current that generates its own poloidal magnetic field. You can confine the plasma better if you give it some form of a spiral rotational action. So that field here, the poloidal field, is follows the shape of the toroid, but the magnets that you add, which we call the toroidal field coils or toroidal field magnets, generate another magnetic field. And that magnetic field is parallel to the current in the plasma. So you now have two magnetic fields, one that rotates around the circumference of the toroid, and another one from the magnets that goes along the plasma current itself. The two of them combine together and give your plasma a helical or a spiral shape. And in that case, it can be confined without hitting the walls of the container. And this is in essence a configuration of what we call the tokamak. It's a very large transformer, and you add to it another set of coils here on top and on the outside that are called the vertical field coils to cancel the higher magnetic field near the center than the outside. The transformers also can be built as a transformer in the center here. That's a transformer coil that heats the rotating plasma surrounded by those magnets. In that case, what you play with is, in the Lawson criterion, is the tau sub E, the energy confinement time. You want to maintain the plasma for as long as possible, even though you are using a low density compared to inertial confinement. If we use the tokamak, it's nice for experiments, obviously, but there is very little room in the center. So the engineers came out with a suggestion of generating the magnetic field configuration that is spiral in fashion by having a coil moving around the plasma, or a set of coils, as a matter of fact. So you have here the toroid, you still have the magnetic field coils, but you have wires instead of the transformer. So in that case, the center of the device is wide, and you can have basically power converting equipment near the center. So if you put in wires and you circulate them in a spiral fashion around the plasma, you change the shape of a plasma here. This is the shape of the plasma. And in that case, you can confine the plasma better by having it rotate into a spiral fashion. Or you can combine those wires and the magnetic field by a single configuration of the magnets around the plasma. And the plasma in that case does not take the shape of a circular toroid, but it takes almost the shape of a filament, as you could see here, but it becomes a nightmare in terms of designing those magnets using, of course, drafting equipment in that case. So in that case, you find that the stellarator is a device that has lots of room in the center. Compare that to the tokamak, which has almost no room in the center. So it's nice for experiments, but where do you place your power producing equipment there and circulate the coolant in an actual reactor? So stellarator seems to be the engineering choice, whereas the scientific choice for magnetic confinement fusion is the tokamak. This is an actual stellarator, and you could see how the coils are shaped here in that shape. These are the hands of one engineer working on it, and this is another engineer working on it too. And you could see here the shape of the plasma. It's not a toroid anymore, but it takes the shape of the magnetic coils that can lead to a confinement of the plasma. All right, so in that case, the plasma vessel takes a very interesting shape. It's quite large in size, and this is basically a tokamak now, not a stellarator. The previous picture is a stellarator in a lab in Germany. That is Wendelstein in Germany. This is the picture of the interior of the tokamak at the Cadarache Center in France, where the ITER device, or the International Tokamak Experimental Reactor, has been built and it's ready for operation. You could see the interior of the torus here, and this would be antennas that would heat the plasma, not just by transformer action, but also microwave action. And I'll stop here and finish the chapter in the next lecture. I'll remain available in the chat room for anybody who has questions. Otherwise, everybody have a nice afternoon. Thank you, Anchal. Thank you, Alvaro. You can be excused.
Thank you, Professor.
Have a nice afternoon, everybody. This time we didn't lose much, a large part of the video, but we have